Okay. Okay, hello everybody. The last part of our class is to take more about time. So technically, we're just looking in this class, we're looking at some thermodynamic properties of systems that can be measured. Things that are measured daily and we take for granted. Okay. We know what state functions are. State functions are those things that depend, you're going from state A to B. State functions are those that depend only on the initial state and on the final state. The properties of A and the properties of B, they do not depend on how you got the displacement as an example. Okay, so let's start. Internal energy is an example of a state function. Variables of states P, V, and T, number of moles, and so on and so. So the variables of any state can be related by what we call equation of states. An example is PV equals nRT, which is our equation of state for the ideal gas. I want to believe that we have this slide because I sent it the week before, I think last week or so. And so last week we didn't have a class because of matriculation. There are direct entry people amongst us. So one of the things about equation of states is that if you know two of them, you can always get the third. Means if a state function, as an example, can be represented as u being a function of p, p, t, or to make life easy, we usually represent it as a function of two of them, whether PV or PT or VT. It's been observed that if you simply represent it as a function of V and T, our life will be much easier. So let's consider U being a function of T and V. We can then write that a change in U, du, will be dTV, PV. So when you have a function that is, if you have that is a function of two different variables, and if you want to see how it varies with its variables, you keep one constant, du dt, and vary one. So we're keeping v constant, du dt at constant v, plus du dv at constant t. So that is what we can do with what we call our state functions. And this is an exact differential. This cannot be done with path functions, and those are inexact differentials. Anyway, so let's move on. Du dt, we have already talked about that. That's its capacity at constant volume. What about this one? This is called the internal pressure of a system. And that's the units of pressure. So that's the unit that I have here. If you look at it, joule over meter cube. Playing around, you arrive at the unit of pressure. It's called the internal pressure of a system. The internal pressure of a system can be used to measure deviation from ideal behavior. Behavior. And it's given the symbol pi p. Pi p. That's the symbol for internal pressure. Things to note. Pi t. So what that means is that we can write our exact du differential dv dt pi v pi t dt any. Okay. How is pi t measured? The guy that tried to measure it at first, Williams Joel, James Joel or something. Okay. Is Shah Joel. I can't remember his first name. I think I have it in the notes. So how did he try to measure it? He tried to measure it by putting a gas in a tube, in a sphere, copper sphere, connected the gas to another sphere. One of them was a vacuum. So that means it's expanding an approximate pressure of 0, vacuum. And the gas was pressurized till about 22 atmosphere. Everything was put in a water bath and the temperature was allowed to equilibrate. Let's see what happens. Okay, so this should have drawn my tap. This is a tap. So what did he try to do? Try to measure what happens if a gas expands into vacuum. So this is the temperature setup. If the gas expands into vacuum, what happens? It wants to know whether there will be a temperature change. So aim, when a gas expands, is there temperature change? Unfortunately, he observed no temperature change. And he concluded that when gas expands into vacuum, it doesn't have temperature change. And because of that, pi t is 0. How did he arrive at that conclusion? CVDT. So let's see. We know that the change in internal energy from first law is given by dq dt. So if dq plus dw, dq is a energy change due to heat. And there was no heat change, no temperature change, which is no heat change, meaning that dq equals to 0 or q. Then the gas expands into vacuum. So if you're expanding into vacuum, which means you're expanding a pressure against an external pressure that's equal to 0. If that's the case, work, which equals P dV, is also equal to 0, meaning that our delta U is 0. So if delta U is 0, we want to calculate what CV dt is. We know that CV is not equal to 0. But dt, no temperature change, so that makes this 0. If that's equal to 0, dv is not equal to 0 because you are coming from V to, this is V1 to V2. So it means that, so you know, if you have a product of two things, the other one is 0. So if dv is not equal to 0, that means that pi t is 0. So as far as it's concerned, pi t is equal to 0, according to Joe. The Joe the Joe experiment is called a constant internal energy process. So no, not isentropic. The other one is isentropic, and it's believed to measure temperature change with respect to volume at constant U. So that's what I have here. The T dV at constant U, something called the Joule coefficient. Anyway, Now, was that the case? That wasn't actually the case. Because some other people did the experiments later and found out that there was indeed a temperature change. Delta T is not equal to 0. But why did he observe delta T equals to 0? Because of his experimental setup, which was not very accurate. So some guys did the experiment later and found it. From third law of thermodynamics, we don't need to go into the details. It has been deduced that pi t, what do I call it, internal pressure, is given by that formula. Also, please let us note that formula. The important formulas are the ones that I'm putting. Okay, so let's see. If you calculate using this, an equation of states PV equals nRT for 1 mole, you can calculate the PT by T for an ideal gas. Pi T for an ideal gas is using this equation. Oh, that's correct. Okay. Let me solve it. I didn't write everything. Okay. So from the last slide, I said from third law of thermodynamics, pi t is equal to T, the P, the T at constant V minus P. Please let's follow what I'm writing. So if PV equals nRT, that means that P equals RT over V, and the P, the T will be R over V. So if this is pi T, the P dt is R over V times T minus P. This is what we have here. PV equals to RT over V, R times T over V. So this is equal to P. So that's P minus P. And that's pi T for an ideal gas. Let's see what it is for a van der Waals gas. A van der Waals gas, the equation of state is given as that. You have to calculate pi T for, there are 2 questions here. Calculate pi T using that expression from the third law, and then derive an expression for the change in internal energy. Okay, so let's look at pi T. So P equals nRT over V minus NB minus AN squared over V squared. That means the P, the T will be, so this is constant 0, NR over V minus NB. So T times this will give NR minus P over NV times T. Then minus P. P is nRT minus, so this is P. Sorry, this is P. And this one is the P, the T. This is positive, negative, so we are left with AN squared. So pi T is AN squared. So it is not equal to 0 for a van der Waals gas. Any questions so far? Okay, no question. Am I the only one here? No, I'm not. Okay, the second is derive an expression for a change in internal energy for this gas. Incomplete question. So we're given mu delta T to be that. So, and du dv dt, that's equal to pi p. And we have derived it from the previous answer. So if you plot it into the equation, integral 1 over v dv. So integral of 1 over x squared is 1 over x plus p. So from vf to vi, we have minus 1 over vi plus that. So we see that the internal energy of a real gas is not equal to 0. Conclusion from this, another definition of an ideal gas is the one with 0 internal pressure. So if we plot it, generally, deductions and further consideration. For an ideal gas, which is the one that is referred to a perfect gas, pi t equals to 0. It is possible that pi t is greater than 0 or less than 0 for a real gas, depending on whether the gases are attracting themselves or are repulsing themselves. So that will also depend on the pressure of the system. So it's been observed that if pi t is less than 0, the gases are usually repulsive, or repulsive interactions are dominating. So that's when you have high pressure. And if pi t is greater than 0, attractive forces dominate. Let's also consider okay, please, you have to be more specific how you explain the pi t, how you got the pi t. Let's see. If I understand your question, I will have to go to this slide. And we see, this is the slide, it said we did not derive it in this class. We didn't derive it in this class. I said from third law of thermodynamics, we are not looking at third law in this class. I just said that it has been derived. Sorry, yes, it was derived. It has been derived. Maybe I should write that. It has been derived. That this is the expression of pi t. I was told you to please note that. Okay. Deductions. Okay. More on variations. So we just looked at U varying with V and T, and then we arrived at du dv equals cv dt plus pi t dt. So if we now consider that after varying all this, so maybe you're trying to form a process, then you now vary it with the pressure. Or you now make pressure constant. So that means the u dt at constant p is dt dt at constant t plus so that means adding more constraints. So this is equal to cv plus pi t dv dt. The c dt that's equal to 1. dv dt. This expression is related to what is called the volumetric expansion. The quantity is related to coefficient of thermal expansion, volumetric coefficient of thermal expansion. Whenever you're dealing with gases, expansion is an important thing. Anytime. So that's why we try, the field of thermodynamics tries a lot to understand expansion, especially when dealing with gases. So it describes how the size of an object changes with temperature. Solid and liquid expand slightly. So the people in construction would need to consider how this expansion also takes place. For example, if I don't know if you've noticed when you are driving on a bridge, you would always understand that they put metal to allow the spaces in between slabs. It's to allow for expansion. Expansion is important. So you can consider expansion under constant pressure or under constant temperature. And so this was also defined isothermal compressibility. So you see, this is dV dt at constant P. This is dV dP at constant T. That's because compression and expansion are equally important. So KT, isothermal compressibility, is isobaric compressibility. Okay. Okay, so CV is where we're coming from. So these are just side definitions, CV plus pi t dv dt. So if you put all of it together, we arrive at du dt at constant pressure is CV alpha pi t and V. The internal pressure from future class has also been derived to be related to alpha kt. Okay, let's look at an example. So these are just things to read. What is the isothermal compressibility gas factor for an ideal gas at 1.0 atmosphere? Isothermal compressibility, that's the kappa T given by the formula. Ideal gas equation PV equals nRT, meaning that if you make V the subject of the formula, V is nRT over P. So the V, the P, is differentiates this with respect to P. That gives us nRT constant P minus 1, that's minus 2. We have nRT over P squared, which is minus V over P because V is nRT over P. Let's put it all with that. KT is minus 1 over V, dV, V. So minus 1 times, this is minus 1 over V, which is this minus 1 over V, times V over P, because V over minus V over P is this as derived from here. V cancels out, minus becomes positive 1 over P. So we arrive at 1 ATM reciprocal. Question? Okay, let's play around a little bit more. I think we already derived Cp minus Cv equals to R. And I hope we recall that we are talking about molar heat capacity. So for n mole, then we have to incorporate number of moles into one place in there. Okay. So what's the relationship between Cp? How can we express the relationship of Cp and Cv in terms of our pi t, alpha, and kappa t? So one expression, we already know that dp, this is equal to, let's play around a little bit with mathematics. So Cp minus Cv gives the h dt at constant p minus the u dt at constant v. Recalling that h equals to u plus v, and putting it in that equation, we arrive at du dt at constant place plus p dv dt minus p du dt. But because we are dealing with constant pressure. And we have already, in the previous slides, obtained du dt to be c to be this. And we know that Cv equals that. So if we put this in here and this in here, du, so let's put this in here first. So we see that Cp minus Cv, du dt at constant p, this is it. So this is du dt at constant p plus p dv dt minus du dt. This is Cv. Cv minus Cv. So we are left with pi t dv dt plus p dv dt. This can come out factorization. So this is one expression. Does that mean this is equal to R? I leave you to that. And because we said that this has been derived, let's annoy each other a little bit more. So if you put pi t, expression for pi t in that equation, we get, sorry, this is not pi t. There's an error here. Okay, anyway, this is the equations to note. This one and this one. This error is due to copy and pasting. So if we put pi t in this equation, we will arrive at this. So let me just quickly do it. So that's t dp dt, it's constant v, minus p, then plus this p into alpha v. How did we arrive at that? So this is supposed to be Cp minus Cv. Recall, alpha is 1 over v dv dt. meaning that dV dt is alpha times V. So we saw put that in there. So this is one expression, another expression, and the one that we already know, Cp minus Cv equals to R. The way we did it for internal energy, also a state function. Let's consider for and considering that H is a function of T and P. Why are these ones convenient? H usually is often measured at constant pressure, and that's why, remember, it's equal to Q at constant pressure, U is Q at constant volume. So it's convenient to work with V for U and P for H. Anyway, so we can express the H dt as so. And if you express it as so, Cp dt dH dt dt. If we consider an isenthalpic process, that means this is equal to 0. The H dP considering an isenthalpic process means that we have this to be equal to 0. And we make the H dt the subject of the formula. We have the H dP equals to, taking this to this side, that's minus Cp dt, dividing by dP throughout constant enthalpy, because we said if we have an isenthalpic process. This thing is called Joule-Thomson coefficient. It's a very important parameter in the cooling of gases, up till what we use in our refrigerators nowadays. The ratio of the infinitesimal change in two intensive properties, and it's also an intensive property. Thus, the H Cp minus, and putting it all into this expression. Let's play with the Joule-Thomson coefficient a little. Said 40 minutes. I've not spent 40 minutes. Joule-Thomson experiment was used to measure mu Jt. I don't have the picture. I'll put, sorry. So the setup involves forcing a gas through a throttle process. I'm surprised I don't have the picture. And observing what changes, keeping H constant, observing what changes with temperature and all that. Anyway, what was really observed, which is what I would focus on. I can reshare the slide with the picture of the experiment. So a gas is allowed to flow very slowly from a region of constant pressure to a region at constant pressure P2. There are two different pressures through a porous plug, and the temperature change is monitored. That's because we already said our mu Jc is equal to dt dP at constant H. So the temperature is monitored as you're going from P1 to P2. Remember, for that of Joule experiment, it was the volume change that was observed with temperature, du, dt, dV at constant U. That was what was observed. Now that's also applicable to gases. Anyway, so what was observed here in this case is we have a general observation that when a temperature and pressure curve, this is the usual curve that you see. If you plot, if you on a temperature and pressure, when looking at d, T, d, P, the curve always goes like that, whichever way. Whether, say, for example, whether it's big or small, but it goes like this. For an ideal gas, what's the general observation? That's what we are going to deal with. Is that mu Jt is always equal to 0, meaning there was no temperature change observed when the gas was ideal. You know, you can approach ideality in low pressures and high temperature, or in short, just infinite dilution. The gas is not they are not interacting. When you have a pressure such that the gases are not interacting, you are approaching ideality, low pressure. Okay. However, for real gases, that's not what was observed. For a real gas, it was observed that your mu Jt can either be less than 0 or greater than 0. So this is the curve. When mu Jt is equal to 0, is less than 0, it's inside this shaded area. And outside here, mu Jt is greater than 0 here. And outside here, it's less than 0. And it moves at each enthalpy. It moves to, it changes sign at certain temperature. So if mu Jt is greater than 0, attractive forces dominates. If it is less than 0, repulsive forces dominate, and the gas cool attractive forces dominate, gas cools on expansion at constant enthalpy. If mu Jt is less than 0, gas heats up in expansion. So as the gas is expanding, it is generating heat. Regardless, anything could have happened. So the temperature at which mu Jt is called the inversion temperature. So if we are considering a certain temperature, then you would know. Along the boundary, gas will undergo neither a temperature or, so the values here along this boundary the gas will neither there will be no temperature change on expansion. It cools and then it heats up here. So these are examples. This is the mu Jt curve for nitrogen. This is mu Jt for hydrogen. This one is for helium. So depending on the condition for a given temperature, a particular gas may show cooling effect at one temperature and heating effect at another temperature. So here, at such temperatures, at this temperature, temperatures around here, nitrogen will cool. Temperatures around here, nitrogen will heat up. These are called the upper and lower inversion temperature. And it found application again, like I said, in anything that involves cooling. The one that comes to the top of my head is the refrigerator that we all use in our homes. And even in AC, and in some places where they use heater, you consider that. So the gas that you will use at such temperature will depend on the property of that gas. So that's why we said at the beginning of the class, there are some properties of gases that usually observe, and the thermodynamics helps us with the different applications. Okay, let's work an example, and I think after the example, we are calling it a class. Okay. A vapor at 22.8 atmosphere was allowed to expand adiabatically to a final pressure of this. The temperature fell by 10 Kelvin. Calculate the Joule-Thomson coefficient at 5 degrees, assuming it remains constant over this temperature range. Joule-Thomson coefficient is dP, dt, which is approximately change in temperature, that's 10 Kelvin, and change in pressure, that's that's supposed to be 22 minus 1. So 10 divided by 22 gives us 0.4. And there's another example. The volume of a certain liquid varies with temperature as that V prime into 0.7 times 3.7, where V prime is its volume at 298. Calculate its expansion coefficient alpha. At 310 Kelvin. Alpha is defined by that expression. So what's dV dP? dV dt this is constant, it's not given, it's not going to be occur. This is with respect to t squared, so we have t over v for the whole full expression. Plot in the value of temperature and calculate alpha. Why is mu j? It's the properties of nitrogen. That's why. There are some, if you consider, for example, if you remember when you were talking about real gases in using van der Waals equation, what characterizes them is A and B. What are the A and B for nitrogen and hydrogen? So it's all these properties that people consider, like I said, when developing any form of application. For example, anybody that wants to develop there was a seminar that I attended one time on developing catalytic converters for the exhaust of cars. So you have to be able to consider which one can be absorbed, which solids can absorb and purify the combustion out better. So you have to check a whole lot of parameters before you arrive at one. So exactly why nitrogen is more pronounced is dependent on the property of nitrogen. Take, for example, nitrogen exists as a diatomic atom. It is way bigger than hydrogen and helium together. Where is that our slide? So we have N2, hydrogen, 2. Helium is a monoatomic gas, even though He is atomic number 2. This one proves to be heavier than that, and that's way heavier than that. If you can Google and see the mu-J-T for different elements, you would see the different graphs. I hope I was able to understand, explain that. Any other question? So we will most likely have our test on Friday next week.
Hmm?
Hmm? I already told you that we will have tests, so we'll discuss with the other lecturers, and it's probably going to be a combined one. I will let you know whether it will be online or physical. Any other question? Thank you.